This last example is going to span many, many pages, and it's going to put together everything we've learned so far about basic probabilities into one example and expand our understanding of a few things. So this is going to be with a coin and a die. So we have a probability experiment that consists of tossing a coin, which has a heads or a tails, and then a six-sided die. And we can do this online with an online simulator as well. So you can roll the die right here and then toss the coin or flip the coin. And there you have it. So that's tails and that's a 3. All right, so either way you like it, do whatever you like. So how large is the sample space? Okay, well, a coin has 2 sides, right? And this is a Hong Kong $2 coin, in case you're interested, from 1975, back when it was under British rule, hence Queen Elizabeth on the front. So the coin, let's use that multiplication rule of counting here. So I always like to give little slots. So there's a coin slot and there's a die slot. The coin has 2 outcomes and the die has 6 outcomes. 2 times 6 makes 12. So there's 12 outcomes. That is the size of the sample space, which is what was being asked. When they say how large is it, that's what they want to know. Not what is the sample space, but that's coming. All right, so now let's construct that sample space with your favorite in mind, a tree diagram. All right, now we have an order implied here. We're actually going to toss the coin first and then the six-sided die. So the coin is first, the die is second, and that's going to matter for our tree diagram. So down here in the tree diagram, we want to think about the possible outcomes. Well, for a coin, there's heads and tails. So I'm going to, now think about how we do tree diagrams. You make your heads up here, put an H for heads. Tails down here, they're vertically aligned and they've got some space in them because you're going to have to fit the branches for the die. And then you always make a V that goes back to the present. Right? That's not there for its health. It has to be there. There has to be a V going this way. All right, now the die. So after you've tossed the coin and you pick up the die, there's 6 options. 1, 2, 3, 4, 5, 6. So you're going to list them in vertical order. 1, 2, 3, 4, 5, 6. So that could come from the heads. And you have to make this kind of V shape coming back. These are called branches. But it also could come from the tails. So you have to make another 1, 2, 3, 4, 5, 6. And make it branch from the T to those values. And by the time we're done, we have 6, 7, 8, 9, 10, 11, 12 outcomes, just like we said we would. But of course we're not done because the sample space has to be listed. So I'm going to list it right now. So sample space is listed over here, because a tree diagram is not complete until you have each one of these going somewhere. So H1, and then this 2 was H2, this 3 was H3, H4, H5, H6. This 1 was a T, right? So T to 1, T to 2, and so on. So each one of these values here at the end gets associated with a value or a label in the sample space. And there we have it. That's our sample space. Now the classical probability of tossing H1, right, heads 1, is 1 outcome out of the 12 outcomes here. So the probability of H1 is 1 out of 12, which would be, let me grab Desmos. All right, 1 out of 12. 0.083 repeating. Since I'm rounding, I'm going to do an approximation sign because I've rounded it to 3 decimal places like that. Okay, so now I want to actually experiment. And you can do this along. You can play along yourself. You don't have to circle my values. So we're going to toss a coin and a die yourself. And I got tails and a 5. So I'm going to circle tails 5, but you could also go to that online site and get your own values. So you can roll your die and flip your coin and see what you get. Tails 3 is what that one was for me. But circle whichever values you get. It's fine. All right. Now, how many of the trials were H1 in the class overall? So I've actually done this with a class and I tracked the data. So we're just going to have to use the data from my particular class. So in my class, there was only one student on the first trial that was H1 out of the 20 students that were there that day. So that makes the the empirical probability, because this is from data, 1 out of 20, which is 0.05. Isn't that interesting? Okay, so why didn't it work out exactly? Well, that's because, okay, so the classical probability was 1 out of 12. Oh, I should say the probability of H1, sorry. It doesn't really matter the fraction. I'm just going to write the decimal like this. And the empirical probability, the probability of H1 for that class was 0.05. So this one is from logic. This one is from real life. Right? Real life is messy and random. Right? Real life just, it's messy, it's random. It doesn't work out the way that we think logically it should every time. It will conform to logic in the long run. That's kind of where I'm going with this. It does not conform to logic perfectly. Right? So this is what it should be, but this is what it actually was. Right? And that's because real life is messy. Now, it's not that far away. It's not like, you know, oh, this was 0.083 and this was 82%. It's not like that. It's that they're close, right? But it's not perfect. The values are close, relatively speaking. All right, so let's do it again. So I tossed my coin and my die, and I got heads 3 that time. So I'm going to circle heads 3. I love this coin. It's so fascinating. I love the wavy edges on it. All right, so how many trials of the experiment were H1 this time? So this time I had 2 out of my class of 20. So that makes 2 out of 20. Again, it's an empirical probability here because it's from data. And that was 0.10. So let's compare the empirical probability we found here with the previous one. Are they the same? And the answer is nope. Right? So the first empirical probability we found was 0.05. But the second empirical probability was 0.10. And that's because, again, real life is messy and random. It's not going to be perfect every time. So, and I mentioned this in the definition for empirical probabilities. Actually, let me back up real quickly. So, in the definition for empirical probabilities, it said they vary from data set to data set, right here. They're not always the same. Empirical probabilities aren't, because they're from real data. So because the empirical probabilities are from real life, they vary from trial to trial. right? Because each time we pick up the die and the coin and we toss it, that's a trial. It's called the trial of a probability experiment. And that's because real life is messy and random, what I wrote above. Again, they're close, right? It's not that they're super far apart. It's not like this is 0.05 and this is 0.81. That's not what's happening here. But note the values are close. I should have put that here. Those values, I was meaning those values, 0.03, 0.083 and 0.05. They're close, close-ish. Same thing with down here, right? They're not the same. That's okay. The classical probability, by the way, is still 0.083. That never changes, right? So the classical probability never changes. It's locked in stone as 0.083, right? So it is what it is. It will never change, right? This will never change unless you change the whole experiment, right? But for this experiment, that will never change. But these values will change based on which problem you're doing, or which experiment you're doing, I should say. So every time you do it over and over, it's going to change. It might be 1 again, it might be 0, it might be 2, etc. And that's because they come from real life, and real life is messy. Classical is not messy. Classical just is what it is. It's the previous page. When we establish this, this is classical. This is just locked in stone. That's the way it is, period. This will never change. But empirical, it's from actually tossing a die and a coin, so it's going to be messy. It's going to be different. It's going to have variation.